All right, so this section is called counting rules. So in this section, we learn how to count and find a sample space when it's too large to find, listen or not. So that's a key thing when it comes to it. This section, we're finding the sample space always. So for instance, remember we talked about way back in the section 5.1, or the basic probability section, where we were figuring out, the sample space of, 4 children, and it said if you go on, well, what if I want like 10 children, right? So what's the probability of getting, I don't know, like 5 kids out of 10, 5 boys out of 10 births. Instead of saying boy, 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 and getting all the combinations, instead of listening to them, we want to figure out is there a way we can do that using the counting rules itself. Okay, and that's what we're going to be learning in this section. You're learning how to count. So give you guys a scenario. Let's do this. So let's suppose you have a restaurant, or you go to a restaurant, and it has this on the menu. It has 3 appetizers, wings, nachos, and mozzarella sticks. 4 entrees, so steak, chicken, lamb, and duck, and 3 desserts, cheesecake, ice cream, flan. So this all tastes pretty good, right? So the question then becomes, how many different combinations can you actually do with this, right? When it comes, so you can go, for instance, one combination would be wings, lamb, and ice cream. Another one would be wings, chicken, and flan, right? So again, instead of listing them all, is there a possible way just to get a number instead of having to figure out, list them all out and then counting how many we actually have, okay? And that's what we're going to be learning here. And the very, very important one is called the fundamental rule of counting. Okay? So it says for a sequence of 2 events in which the first event can occur m ways and the second event can occur n ways, the events together can occur of m times n different ways. Okay? So what that means is we're multiplying each individual possibility together and get our total one. So going back to our example up here and figure out how many combinations are possible. So what we're going to do is how many appetizers we have, how many entrees, and how many desserts we have. So according to our appetizers, how many can we choose from? So we can choose for a total of 3 of them. For the entrees, how many total can we choose from? And that's going to be 4. And then how many desserts can we choose from? And that's 3. So according to this function method of counting is all I'm going to do is multiply all the choices we actually have individually to get our end result. So it'd be 3 times 4 times 3 gives you a total of 24 combinations. Which means is if I literally make a list of all of these out, like I said before, like wings, chicken, and ice cream, that's 1, wings, lamb, and flan, and just go it all the way out, you get a total of 24 combinations. Now notice it makes it much easier. Now instead of listing them, now we get an exact equation based off that information, right? Makes it much easier. Now again, remember, this whole part is just getting these sample space. So we want to find the probability. This number is going to be in the bottom, right? This is the sample space itself we're going to be using. Okay. So let's do a couple more examples so you can see how this will work out, and it makes it much easier to deal with. Okay. So question 1 says, well, at the time I was doing, making this question, I believe there's now 8 of them, but in this question is, there are 7 books in the Harry Potter series. If the books are read in a randomly selected order, what is the probability that they are read in the order and they were written in? All right, so the first thing we want to find the sample space, right? How many orders we can do, right? So for example, we want to read them in, the Sorcerer's Stone all the way to the Deathly Hallows Part 2, right? So that order. So to find the sample space, we're going to use the fundamental theorem of counting to help us out. Okay, so let's give you a scenario. Let's suppose I have all 7 books in my hand and I throw them on the floor and I just blindfold myself. So how many choices do I have for my first book to pick up? 7, right? 7 different choices. Okay, I read it, I put it to the side, and I choose again. So how many more choices do I have left over? And that's going to be 6, right? And notice, keep going down. So I read that book, I put it to the side. How many choices for my third book? So 5, fourth book, 5th book, 6th book, and then finally, last book, right? So according to the fundamental theory of counting is, all I'm going to do is multiply all of these numbers together. And that gives you how many combinations we would actually have, or the sample space. So this should be a roughly 5,040, I believe. So there's 5,040 different combinations of reading the Harry Potter series. Crazy, huh? You'll be here forever if you actually want to list them all out when it comes to it. But again, this is a faster way to find the sample space itself. Now remember, we're not done yet because it asks us for the probability. So the probability would be 1 over 5,040. And for this one, you can leave it as a fraction because a lot of the times these will be very, very small numbers itself when it comes to it. Okay. So let's go another one, question 2 now. So with a short time remaining in a day, a FedEx driver has time to make deliveries at 3 locations among the 8 locations remaining. So you can only go to 3 locations. How many different routes are possible? So just like the last one, you can only go to 3 routes, right? There's basically 3 houses you can go to. All right. For his first house, how many locations can he choose from? 8 of them, right? So a total of 8 locations to choose from. Okay, he went to that house. For his second house, how many locations can he choose from? Now here's a trick question. Right? It won't be 8 because he was not going to go to the same house again, right? So it's going to be 7. Okay. All right, for your last house, how many locations can he choose after he finished 2? 6, right? Now notice it's different than this. Right? This 7 went from 7 all the way to 1. Why is it not here? Because I can only go to 3 locations, right? It's 3 houses. I'm not going to all 8 of them. I'm only going to 3 locations. So meaning that's all we want, 3 locations. These are the ones we can choose from. So now we just multiply, and this should give you 336 routes possible, or different routes. And there we go. And let's try one more using this rule here. So question 3 is a combination lock uses 3 numbers between 0 and 49 with repetitions. And they must be selected in the correct sequence, right? So it's literally combination lock. You turn right, turn left, turn right again, that kind of stuff. How many different combinations are possible? All right. So like I said, right, it's a 3 lock combination. So you have to get 3 correct numbers. Okay. Now the numbers between 0 and 49. So that's a trick question. It's including 0. So you actually have 50 total numbers when it comes to it, right? So for your first choice, how many numbers can you choose from? 50, right, total. Now here's a trick question. It says with repeats. So for my second choice, how many numbers can I choose from? And it's not 49, right? Because I could technically repeat it. So I can have like 0, 0, 0 as a combination. So I could have 50 more. And then for your third choice is the same, right? 50 as well. So again, according to the fundamental theorem, I multiply, and it gives us a grand total of 125,000 different combinations. Crazy, huh? So essentially, the probability of you getting, your lock correctly is 1 divided by that number, which is very, very, very small, right? Pretty much never going to happen itself when it comes to it. Okay. Interesting stuff. So that's using the fundamental rule of counting, right? The multiplication stuff, things like that. So now we're going to learn a different way of counting as well. So we're going to skip this factorial because we're going to use a calculator for that portion. Okay. So what we're going to do now is this concept down here. So what we can do is, let's suppose you have an urn of, let's say, 50 marbles, okay? And we want to choose 10 of those marbles. So I have a bag of 50 marbles, and I'm choosing 10. The question now becomes, how many ways can I choose those 10 marbles out of the 50? So I can have 5 reds and 5 blues. How many different arrangements can I actually have? That's going to be pretty messy, counting those. So now the question becomes, again, like the last one, what equations can we use to help ourselves out? So that's the main focus we're dealing with is, given n objects, we want to choose r of them, okay? And again, I gave you this little scenario here, right? So we want to pick 5 marbles, or no, 13 marbles. How many ways can we choose from doing that kind of stuff? And then for that, we have 2 very special definitions we're going to talk about, okay? It's called permutations and combinations. So permutations, so the first one is permutation. So permutations is an arrangement in which different sequences of the same items are counted separately. Key thing, okay? So when you're choosing R objects from N objects. So in other words, the biggest takeaway you want to do is order does matter how this comes into play, okay? So if you flip the page, we get the equation for permutations. Now in your calculator, it's going to look like this when it comes to it, okay? And I'll talk about a calculator in a little bit, all right? So so this is the equation for permutations with order matters. Now combinations is very similar. It is an arrangement in which different sequences of the same items are not counted separately. That's the key thing when it comes to it. That's the only difference between this and the last definition, where you're choosing R objects from N objects. Or in other words, order does not matter. Okay? So which means the order in which you're choosing the items do not matter. However, when it comes to permutations, the order in which you choose them does actually matter. Okay. All right, so I'm going to skip this portion here and go down to here. So for these formulas, you don't have to use a calculator. There's no other choice around it. And depending on your calculator, it depends on where you're going to see them. So I try to give you guys, I make a video showing you guys the different ways of getting the calculator so you can see that as well. But you can always look at here, it makes it straightforward. Okay. So when it comes to certain type of calculators, for example, like these, you're going to have to go to the math button. So if you go to the math button, which is sometimes here or better in the calculator, you're going to have to go all the way to the probability. So you just scroll, there's your probability, and then you notice there's a P and C there when it comes to it. Most other calculators have it already on there. So have a probability portion. So like I said here. So if you have this type of calculator itself, notice you have a probability button, and it's right there. And some other ones, you have them on here, I believe. You just press second in there. But I may make a video showing you guys the different types. Okay. So what we want to do now is show you guys how you actually use these kind of stuff. Okay.